in this class I will discuss very important topic of engineering mathematics 1, and that is error and approximations. So this is part of the paper, and which is engineering mathematics, and this is a part of differential calculus 1. In this introduction or introduction of error and approximations, let we have some example here. Let in a class any class teacher said to the student that you have to multiply 5 in 6, but the student mistake that one student out of all the student multiplied by 4 in 6. Then what happened? The wrong answer will be 30 minus 24. It means suppose we have to multiply 5 with 6, then we get 30. But one student done a mistake and he multiplied 4 with 6, then the resultant will be 24. Then the wrong answer will be 24. What is the difference between these two answers? 30 minus 24, and that is 6. So this is actually part of error, and error may be any type, and computational error, percentage error, relative error, and etc. So this is actually the part of approximate error he has done. Now let we have any function u, and that is function of xy, and let delta x and delta y be the small changes made in x and y respectively, and the resulting change in the function u is given by the delta u, and which is the change in the value of u. So if u as a function of xy, then the small changes in x and y are delta x and delta y, then the function delta u will be u x plus delta x, y plus delta y, and minus the actual value which is u x y. Now if we add something, and that is actually u x y plus delta y, and subtract u x y plus delta y, then we get the value, and which is u x plus delta x, y plus delta y, minus u x y plus delta y, and plus u x plus x y plus delta y, and minus u x y. Now if we define the value which is limiting the value of delta x tending to 0, we have u x plus delta x, y plus delta y, and minus u x y plus delta y upon delta x, and this is the del u upon del x. So partial differentiation of u with respect to x. And similarly we have the limiting value of y, and that is tending to 0, or delta y tending to 0, u x y plus delta y, and minus u x y upon delta y, and which is del u upon del y. Now if we apply the limits in the relation, then we get delta u equals to del u upon del x, delta x plus del u upon del y, delta y. So we get this value here. So this is the approximate value of u. If we have small changes in the value of x, which is delta x, and a small change in the value of y, which is delta y, then the corresponding change in the value of u will be delta y, which is del u upon del x, delta x plus del u upon del y, delta y. Now if we have done the value approximately, if delta x and delta y are taking as very small errors in the measuring of x and y, then delta u will be the very small change or error in the value of u. Then the approximate value of function f x plus delta x, y plus delta y will be f x y plus del u upon del x, delta x plus del u upon del y, delta y, and this is the approximate error in value of f or u. We have u as a function of x y, then we have formula for u, and here if we have function f as a function of x y, then we get the approximate value of that function will be this one, and this part is actually approximate error in the function if we have small changes delta x and delta y in the values of x and y respectively. Now suppose we have x as any function of x as any function, suppose we have distance, then the approximate absolute error in x will be delta x, and the relative error in x will be delta x upon x, and the percentage error in value of x will be delta x upon x into 100, where x is exact value of the variable and delta x is the absolute error or approximate value of variable x. Now we have two kind of problems here. First one is if we have formula as given for any variable in terms of independent variables, and another one is formula is not given, then what we have to do here? Suppose we have any example here. First one is we have to compute an approximate value of 1.04 whole power 3.01. Then first we have to assume a function of this form, and that is, let we have fxy equals to x is per y. And now we have to assume the values of x and y, and that is nearby value of this one, and which will be any integral value we can take. Let x equals to 1 and y will be 3. Now we have to assume the values of delta x and delta y, and delta x will be 0.4. So that the sum of these delta x and x should be this 1.04. And similarly, we have delta y, which is 0.01, and sum of this value y, which is 3, and 3 plus 0.01, and this should be 3.01. So we have considered a function fxy, which is x is of y, where x equals to 1, y equals to 3, and the approximate values or absolute error in the value of x will be 0.04, and in value of y will be 0.01 here. Now the approximate error in the value of f will be delta f equals to del f upon del x delta x plus del f upon del y delta y. Now first we have to find the values of del f upon del x and del f upon del y. Since we have f as a function of xy, and that is x is per y. So if we differentiate this function with respect to x, then we get y will be treated as constant. So we have y and x is per y minus 1. So this is del f upon del x, which is y into x is per y minus 1. We are differentiating partially with respect to y, then x will be constant here. Now if x is constant, then we get the function which is constant is per variable, which is x is per y. So we have x is y and logarithm of x. So these are partial differentiations of f with respect to x and y here. So the value of del f, which is del f upon del x, and we have y, x is per y minus 1, and delta x, and del f upon del y is x is per y and logarithm of x into delta y. Now first we have to find the value of delta f, and delta f will be here. Since we have x as 1, y as 3, and delta x as 0.04 and delta y as 0.01, then we get delta f, which is 3 into 1 raised to 3 minus 1 and 0.04. And since we have logarithm of x, x means since x is 1 here, so logarithm of 1 will be 0. So the value of this delta f will be 3 into 1 raised to 3 minus 1, since we have this one as 3 into 1 raised to 3 minus 1, and the value of delta x is 0.04, and the second term is we have x is for y, x raised to y means 1 raised to 3, and we have logarithm of 1. Then we have delta y, and delta y is 0.01 here. So since this term is 0, so this whole term will be 0 here. So now the value of delta f will be 0.12 approximately. But here we have to find approximate value of the given expression, and which is 1.04 whole power 3.01. Now the value of this function will be f x plus delta x and y plus delta y. So approximate value of this function will be fxy plus approximate error in that function, and which is delta f. So this is delta f. So we have f plus delta, this term is actually delta f. So now the value of this whole expression will be the fxy. Fxy means since function is x is per y, so and the value of x is 1 here and value of y is 3 here. So this is 1 actually. So this term is 1 here. This term is 1 and this term is 0.12. So after adding these two values, we get 1 plus 0.12. Finally, we have 1.12, and which is the approximate value of given expression. So if we have approximate error, then this is delta f. We are talking about approximate error, this is delta f. And if we are talking about the approximate value of function, then this is actually the function fxy and plus delta f. So this is the approximate value of the given function, which is 1.12. Now we have one more example here, in which we have to find the possible percentage error in computing the parallel resistances R of three resistances R1, R2 and R3, and we have a relation which is 1 upon R plus equals to 1 upon R1 plus 1 upon R2 plus 1 upon R3. If R1, R2 and R3 are each in error by 1.2%, and this is positive error of 1.2%, then we have to find the possible percentage error in computing the parallel resistance R. So here we have to find percentage error in R, and the percentage errors in R1, R2 and R3 are given here. So what we have to do here, first we have to take the relation which is 1 upon R equals to 1 upon R1 plus 1 upon R2 plus 1 upon R3. Then if we differentiate this one, then we get, as we know, the differential of 1 upon x. 1 upon x means we have x is power minus 1. If we differentiate this function, then we get minus x is power minus 2, or we have minus 1 upon x square. So this is the differential of 1 upon x with respect to x. So we are differentiating R. Then we get delta R upon R square. So if we differentiating this function with respect to x, then we get this one. Or differential of this one will be minus 1 upon x square, then we have delta x. This is differential of x. So we are taking differential of 1 upon R, we get minus 1 upon R square into delta R. And similarly, we have differential of 1 upon R1, which is minus 1 upon R1 square and delta R1. And similarly, we have differential of 1 upon R2, which is minus 1 upon R2 square. This is R2 square, and we have delta R2, and minus delta R3 upon R3 square. Now what we have to do? Now if we multiply it by 100, this expression is 100, then we get minus delta R upon R square into 100, minus delta R1 upon R1 square into 100, minus delta R2 upon R2 square into 100, and minus delta R3 upon R3 square into 100. And since we have errors in R1 and R2, R3 are given here. So since we have delta R1 upon R1 into 100, which is 1.2%, and similarly delta R2 upon R2 into 100, which is also 1.2%, and error in R3, which is delta R3 upon R3 into 100, which is also 1.2%. So these are the errors or percentage errors in R1, R2 and R3. So now if we simplify this one, as we have minus 1 as common here, so we can cancel out this one as, and so we get delta R upon R square into 100, and this is square here. So this one is plus here. So now we'll discuss later this one. So we have delta R upon R square into 100 equals to delta R1 upon R1 square into 100 plus delta R2 upon R2 square into 100 and plus delta R3 upon R3 square into 100. So if we solve this one, or since we are having here delta R1 upon R1 into 100 as 1.2%, so we can write this one as 1 upon R1 into delta R1 upon R1 into 100, and similarly we have 1 upon R2 into 1 upon R2, and we have delta R2 into 100, and similarly we have 1 upon R3 and delta R3 upon R3 into 100, and these values are 1.2. This is 1.2, this is also 1.2, this is also 1.2. So we have 1.2, 1.2 and 1.2. So we can take this term as common here. So we take this one as common. So we have 1 upon 1.2 into, and this term will be 1 upon R1. So we have 1 upon R1 plus 1 upon R2 and plus 1 upon R3. So we get the value which is 1.2 into 1 upon R1 plus 1 upon R2 plus 1 upon R3, and this term is actually 1 upon R from starting here. So this is 1 upon R. So finally we have 1 upon R into 1.2, and the left hand side is delta R upon R square into 100. So 1 R is cancelled out here. So finally we get delta R upon R into 100, and which is 1.2. So we get the percentage error in R. So according to question, we have to find possible percentage error in computing the parallel resistance R of three resistances R1, R2 and R3. And we have some relation here, which is 1 upon R equals to 1 upon R1 plus 1 upon R2 plus 1 upon R3. So first we have taken differential of this one expression, multiplied with 100, and since we have percentage errors in R1 and R2 and R3, and these are 1.2% here. So finally we get percentage error in value of R. So now we have one more question here, which is we have to find the percentage error in calculating the area of an ellipse. We have equation of ellipse, which is x square upon a square plus y square upon b square equals to 1, where the error of 1% is made in measuring the major and minor axis here. So if we have any ellipse, an equation is x square upon a square plus y square upon b square, then the area of ellipse will be a equals to pi xy, where x is the length of semi major axis and y is the length of semi minor axis, and this is the area, which is a equals to pi xy. And if we take logarithm on both sides, then we get logarithm of a, which is logarithm of a, equals to logarithm of pi xy. And as we know, logarithm of product of functions equals to sum of logarithm of function. So we get logarithm of pi plus logarithm of x and plus logarithm of y. So we get this one. So logarithm of pi equals to logarithm of x plus logarithm of y. So now if we take differential of this one, so we get logarithm of pi. So if we differentiate this one, we get logarithm of a will be 1 upon a into dA equals to differential of logarithm of pi will be 0. So this is 0 actually, and logarithm of x will be 1 upon x into dx, and differential of logarithm y is 1 upon y into dy. So if we multiply it by 100, we get dA upon a into 100 equals to dx upon x into 100 and plus dy upon y into 100. So this is dA upon a into 100 equals to dx upon x into 100 plus dy upon y into 100. As we have percentage error in major and minor axis as 1%, it means error in x is 1% and error in y is also 1%. So we have error in x, x means dx upon x, this is percentage error, and which is 1%. And similarly, the percentage error in y is dy upon y into 100, and this is also 1%. So these are errors in x and these are 1%. So value of this term is 1% or 1, and this is also 1. So we get 1 plus 1 equals to 2%. So percentage error in area will be 2%. So if we have errors in semi or major and minor axis as 1%, then error in area of ellipse will be 2%. Now we have one more question in which the deflection at the center of a rod of length L and diameter D, supported at its end and loaded at the center with a weight varies as W L cube D raised to minus 4, and what is the percentage increment that in the deflection corresponding to the percentage increases in W, L and D of 3, 2 and 1 respectively. It means if we have some percentage increment in the values of W, L and D as 3%, 2% and 1% respectively, and we have to find the possible percentage increment or decrement in the weight, then what we have to do, since this is given to us that the weight varies as this one, since we have weight as directly proportional to this term, then what we have here, let m equals to this one, it means the weight m is directly proportional to W L cube and D raised to minus 4. So weight varies as W L cube D raised to minus 4. Then what will be the value of m? M will be equals to some proportional constant k and WL cube and d raised power minus 4, or we have m equals to KWL cube d raised power minus 4. So this is the value of m, or weight. So now we have to find the percentage error in this m, and the errors in W, L and D are given to us. The percentage error in W is 3%. It means we have del W upon W into 100, which is 3%. Del L upon L into 100, and which is 2%, and del D upon D into 100, and which is 1%. So these are given. Percentage error in W, L and D are given, and these are 3%, 2% and 1% respectively. And now we have to find the error in n. So first we have to take logarithm on both sides. So if we take logarithm of this function, then what we have? If we take logarithm, then we have logarithm of k. First we have logarithm of k, logarithm of this term. Then we have logarithm of W. Then we have logarithm of L cube. As we have a formula in which we have, suppose we have logarithm of A upon B, then we have logarithm of A and minus logarithm of B. So we have logarithm of this whole expression as we have logarithm of k and plus logarithm of WL cube upon d raised power 4. So we have logarithm of k and plus logarithm of W into logarithm of plus logarithm of L cube and minus logarithm of d raised power 4. And finally we have logarithm of W plus 3 times logarithm of L and minus 4 times logarithm of D. So now here we have to find the percentage increment in m. Here we have to find percentage increment or percentage error in value of m. It means first we have to take differential of this one. So if we differentiate this one, we get 1 upon m delta m, and this is constant here, so this term will be 0. Next we have logarithm of W. It means 1 upon W into delta W, plus we have 3 times logarithm L. It means 1 upon L into delta L, and finally we have minus 4 times logarithm of D. It means 1 upon D into delta D. So we have delta m upon m equals to delta W upon W plus 3 times of delta L upon L and minus 4 times of delta D upon T. Since we have to find percentage error, so multiplied by 100 here. So after multiplication we get this expression. And also we have percentage errors in W, L and D, and these are this term is 3%, this is 3%, and this is 2%, and this is 1%. So put these values here, we get 3%, and we have 3 times of 2% and minus 4 times of 1 here. So finally we have 3 plus 6 minus 4, or we have 5%. So according to question, we have to find the percentage increment or percentage error in deflection, percentage error in weight corresponding to percentage increment in W, L and D, and these are given to us, and these are 3%, 2% and 1% respectively. Now we have one more question here. In estimating the number of bricks in a pile which is measured to be 5 meter by 10 meter and by 5 meter, and the count of bricks is taken as 100 bricks in 1 meter cube, and we have to find the error in the cost when the tape is stretched 2% beyond its standard length. The cost of bricks is given to us, and this is 2000 per rupees 2000 per 1000 bricks here. So here we have to find the error in cost. So if we stretch any tape by 2% or 1%, then what will be the error in cost? It means first we have to find error in measuring the volume of that pile. So what will be the error? Then we can find the error in cost. So first we have to find error in volume, and the volume of any pile, and which will be measured as the volume as length into breadth into height. So first we have to assume what is the length of that pile and breadth and height. So first we have to assume that length is L and which is x, breadth B is Y, and height H is Z. And what will be the volume of that pile? We will be LBH, it means this is X, Y, Z. Now first we have to take logarithm on both sides. If we take logarithm, then we get logarithm of V and equals to logarithm of X plus logarithm of Y plus logarithm of Z. Now if we take differentiation on both sides, then we get 1 upon V into delta V equals to 1 upon X into delta X plus 1 upon Y into delta Y and 1 upon Z into delta Z. So this is differentiation or differential of this expression, which is this one. If we multiply by 100 on both sides, we get delta V upon V into 100, delta X upon X into 100, delta Y upon Y into 100 and delta Z upon Z into 100. So if we stretch any tape by 2%, it means we have error of 2% in measuring any measurement. Like we have length, then tape is also stretched with 2% error, and in measuring breadth, then tape is also stretched with 2% of error, and in measuring the height, the error will also be 2%. So this is 2%, 2% and 2%. So finally we get 2 plus 2 plus 2, it means we have 6%. So this is 6% error in measuring the volume of that pile of bricks. Now the value of delta Y upon V upon 100 equals to 6%. So we have here, suppose we have delta V upon V into 100 and this is 6%. So what will be the value of delta V? Since we have to find error in cost, it means we have to find error in the volume first. So error in volume will be 6 into V upon 100. And what is the V? V is actually the volume of pile of bricks, and V is here 5 into 10 into 5. So this is the volume of that pile of bricks. So what will be the value of delta V here? So delta V will be 15 meter cube or 15 cubic meters. Now the error in volume will be this 5 cubic meter. So we get approximate error in measuring the volume of that pile of bricks. If we find the error in cost of this 15 meter cube, then we get the required error. So first we have to find the number of bricks in this 15 cubic meters. Since we have 100 bricks in 1 meter cube, so number of bricks in these 15 cubic meter or 15 meter cube will be 100 into 15. So we have 100 into 15 equals to 1500. So these are the bricks, or these are the number of bricks 1500, and we get the error in bricks which is 1500. So we get number of bricks in that particular volume, delta V will be 1500. So this is the counting error in bricks. Now we have to find the cost of these 1500 bricks. So error in cost will be 1500. Since cost of one brick is rupees 2000 per 1000. So this is 2 rupees per bricks. So cost of these 1500 bricks will be 1500 into 2000 upon 1000. So this is 1500 upon 1000 into 2000. So finally we get the rupees 3000. So error in the cost of bricks will be 3000 here. So according to question, we have a pile of bricks with measurement these, and they are saying according to question, if we have error in measuring any length like height, breadth and length, we have tape stretched with 2%, then what will be the error in whole volume? First we turn error in whole volume, and that error will be this one, and which is delta V. Delta V means this is 15 meter cube. So first we have find error in estimating the pile of bricks. Then we have to find number of bricks or error in counting the number of bricks, and then we have find error in the volume of these bricks, and this is rupees 3000. Now we have one more example here. According to this example, if the side and angles of a triangle ABC vary in such a way that its circumradius remains constant, then we have to show this one. As we have the circumradius R of a triangle ABC, and which is given to us, and we have some relation here, A upon 2 sin A plus equals to B upon 2 sin B, and equals to C upon 2 sin C equals to R, and R is the circumradius. So according to question, for any triangle ABC, its circumradius remains constant. Remains constant means this R is constant here. Then we have to solve some relation here, which is d small a upon cos A plus d small b upon cos B and d small c upon cos C, where small a, small b and small c are the sides of a triangle, and capital A, capital B and capital C are the angles of that triangle. Now according to this relation, we have A upon 2 sin A equals to capital R, or A will be 2R sin A, and similarly we have B, small b equals to 2R sin B and small c equals to 2R sin C. Then if we differentiate this one, we get d small a equals to 2R sin, differential sign is cos, so we have cos A, and the differential of A will be dA. Since we have R as constant here, so we have d A equals to 2R cos A dA, and dB equals to 2R cos B dB, and dC equals to 2R cos C dC. So if we find here, and this is dA upon cos A, so if we take this one is in this side, so we get dA upon cos A, and equals to, we have 2R d capital A. So this is 2R d capital A, this term is actually 2R d capital A, this term is 2R d capital B, and this term is 2R d capital C. If we take 2R as common, then we get dA plus dB plus dC. And since capital A, capital B and capital C are the angles of a triangle, so we have A plus B plus C and equals to pi. If we differentiate this one, we get dA plus dB plus dC equals to 0, since pi is constant here. So this term is 0 here. So we get dA upon cos A plus dB upon cos B and plus dC upon cos C equals to 0. So in this example, the sides of according to question, we have, if the sides and angles of a triangle ABC varies, so sides varies, it means small a, small b and small c varies, and also the angle varies, but circumradius is constant. So we have taken R as constant here. Then we have to find the value of this expression, and it should be 0 here. And thank you. That's all for this class today.